Okay, so welcome to this next video. Okay, so we've seen that if a neuron is firing continually, then the electrical potential across the membrane of this axon terminal will be continually undergoing action potentials, basically. So you'll get this periodic pattern of electrical potential difference across the membrane. So if we could basically put in a channel, a voltage-gated calcium channel, into the membrane of this axon terminal, which would open every time you got an action potential, then we'd be in business, basically. So what we can do is we can put in such a voltage-gated calcium channel. So here we go. Here is a voltage-gated calcium channel. And voltage-gated calcium channels, again, the pore-forming subunit consists of 4 domains, just like the voltage-gated sodium channel. The pore-forming subunit, it's a single polypeptide. However, again, it's split into these 4 domains, 1, 2, 3, and 4. But it is a single polypeptide. Right, so this time this pore-forming subunit is known as the alpha-1 subunit. And that's because the voltage-gated calcium channels have a whole bunch of auxiliary or accessory subunits. So they have what's known as a gamma subunit that sits off here, which again, it's not essential for the pore-forming subunit, but it does moderate the function of the pore-forming subunit. Then you have a beta subunit down here, and you also have an alpha-2 delta subunit over here. So this is an alpha-2 delta subunit. Okay, so this is the structure of the voltage-gated calcium channel. And basically, every time the electrical potential difference across the membrane goes above some threshold potential for the voltage-gated calcium channel, which will be around -40, similar to the voltage-gated sodium channel and the voltage-gated potassium channel, although the auxiliary subunits will moderate that, they will change that. Basically, this voltage-gated calcium channel will open every time you get to this threshold potential. So let's have a look on this graph where we get to threshold potential. So if this is our threshold potential here, then what's going to happen is we're going to activate these voltage-gated calcium channels continuously. Every time you get an action potential, we are going to be activating these voltage-gated calcium channels. So you're going to get periodic opening of this voltage-gated calcium channel. Now, calcium concentration is much higher extracellularly than it is intracellularly. Calcium concentration extracellularly is generally around 1.5 millimolar, whereas calcium concentration intracellularly is generally around 100 nanomolar. So when you open the voltage-gated calcium channels, the concentration gradient favors the movement of calcium into the cytoplasm of the axon terminal. So you're going to get calcium moving in, and then basically if I was to put a little measuring device, basically, let's say here, that was measuring calcium, and I was to draw a graph of calcium concentration versus time, like so, then what I would see is an oscillatory calcium level within the cell. So I'd see calcium going up when I got an action potential, then I'd have an interlude, calcium would go up again when I saw an action potential, and up again when I saw an action potential. And of course, in between the action potentials, the calcium would be being extruded from the axon terminal by membrane-bound extruders, such as the plasma membrane calcium ATPase, which I'll draw here. So this is the plasma membrane calcium ATPase, and the sodium-calcium exchanger here, NCX. Okay, so they will be extruding the calcium. So when you let in the calcium, it would then fall back to normal cytoplasmic level, basically, because of their activity. Okay, so that's all for this video.